I'll start this video by stating a lemma. It's a lemma we could have proven back in section 5.3, but which we didn't happen to need until now. So you start with a metric space. Of course, we're going to care about the case where x is R2. And we're going to grab two subsets of x. Of course, the case we care about is the case where P and Q are polygons. Of course, this lemma is true. Sorry, Q and R are polygons, but of course this lemma is true for arbitrary subsets of a metric space. And the conclusion is that if you look at the boundary of Q and R, you can see on this picture, every point that's on the boundary of their union is on the boundary of one of the two sets that you started with. So we can write this as the boundary of Q union R that's contained in the boundary of Q union the boundary of R. And conversely, if you look at the points that are on the boundary of Q or R, but are not on the boundary of their union, that's these points here in the middle, those are all, you'll notice they're on the boundary of Q and the boundary of R. So the only points we're missing from the boundary of the union is the points that are on the boundary of both of them. So we can write another inclusion. So boundary of Q union boundary of R, which is bigger than the boundary of their union. And then if we take away the intersection, we get that that is contained in the boundary of their union. I'll leave that as an exam study problem, but this is a purely section 5.3 open closed sets in metric space result. So now let's get back to Green's theorem. Let's recall that we're in the middle of proving that Green's theorem is true in arbitrary polygons, and we've shown that it's true in certain triangles and that you can always put those triangles together to make any polygon. So all we need to prove is the following lemma that says that if Green's theorem is true in two polygons, it's also true in their union. So I'll phrase this a little bit differently from before. I want to use some letters for some different things, but it should be more or less understandable. So let's let QR be two polygons. And we're going to let P be their union. And we're going to suppose that these polygons, we're really putting them together by gluing them along the boundary. So the intersection of the two polygons is equal to the intersection of the boundary. So there can't be any points in the interior of Q that intersect that are also points in the interior of R, or even are points on the boundary of R. And then Green's theorem is true. Let me go ahead and state Green's theorem again. Let's suppose P, which is our union, is contained in some open set U. And we've got a function f, a vector valued function, so its range is R2 not R, that is continuously differentiable. So f is continuous and so is its gradient. And let's suppose that we've got Green's theorem in Q and R. Suppose further that we've got the integral over P of, remember Green's theorem has partial f2 partial x minus partial f1 partial y. That's equal to the integral over the boundary of P of the dot product of f with the tangent vector. And then, of course, we assume the same thing is true in the other polygon. And then the conclusion is that Green's theorem is true in their union. So to prove this lemma, to prove Green's theorem in polygons, we are going to start by thinking a little bit about what the boundaries of our polygons and their union looks like. So remember, a polygon, by definition, its boundary is finitely many line segments. Where each LJ and LK is a closed line segment. And we can require that they intersect only at their endpoints. If you take this polygon, for example, with those 4 edges and then these 4 vertices, what you can go ahead and do is add a new vertex in the middle where the edges cross, and then just declare that this is now a polygon with 6 vertices. So we may require that if you take 2 different edges, then the edges Li and Lj, they intersect only at their endpoints, only at one endpoint. We can write that as number Li intersect Lj equals 1, meaning Li intersect Lj, the number sign is just count the number of points in this set. So this is a set containing at most 1 point. And, or if I is not equal to k, then we require the same thing of the edges of R. What did we say about our polygons Q and R? We said that they intersect only at the boundary And the boundary is this union, so we can distribute the unions. Through what, and we get that the intersection of Q and R is the union of all the intersections of the line segments. And then if you think about it, it's not too hard to prove that any two line segments, either they intersect in a line segment or at one point or no points. So that is empty 1 point or a line segment. It might be all of LJ, it might be all of LK, it might be only part of one or the other. Here is Q, here is R. What we are going to do, and you see that we've got some edges overlapping and some not. What we are going to do is we are going to subdivide all the this edge that overlaps. So Q originally had this one line segment, one long line segment here. Now we're going to think of it as having two line segments, the top one and the bottom one. So we're going to subdivide the LJs, LKs. So I'm going to go ahead and change terminology here. The boundary of Q is the union of, let's call them little lambda j. The boundary of R is the union of the lambda k's. And we are going to require there's still closed line segments, and we're still going to require that they only intersect at the boundary. Then, and any two line segments intersected at most 1 point. And what we're going to do now is we're going to say, we're going to start with all the ones that overlap. We're going to start with this line segment here and this line segment up here. So up to some constant j, then they are the same. Lambda j equals lambda j. And if j is bigger than j or k is bigger than j, then they intersect only at 1 point. Or possibly they don't intersect. They can intersect at their endpoints, but that's it. My claim is that the boundary of P is all of the line segments, that all the non-overlapping line segments. So we started big J instead of starting at 1, and that means we're leaving out all the line segments that are showing up on the boundary of Q and on the boundary of R. Let's prove the claim. And we have that by our useful lemma, we have that the boundary of P is contained in the boundary of Q union the boundary of R. That is to say, it's contained in, we start not at big J, but at 1. But let's see why we can throw away the first bunch of these. If J is strictly less than J, if X is in one of the lambda J's, and is in one of the overlapping line segments, and X is not in any of the non-overlapping line segments, then, well, we've got two possibilities. One possibility is that X is here in the middle of a line segment, and that means that you must have a P on one side, R on one side and Q on the other. And that means that there's some little ball around X that's contained entirely in R union Q that's in P. So X is an interior point. The other possibility is, I suppose, X could be an endpoint, but that means that every other line segment coming out of X, maybe there's only one of them, maybe there's more, but the point is that you've got to alternate between R and Q going around this, because these line segments have to be on the boundary of R and on the boundary of Q. They've got to have them on both sides, and that means, again, you can draw a little neighborhood around X, the biggest neighborhood that doesn't hit any other vertex, any other edge, and it's going to be in Q. So in this case, X is an interior point of P. So that means X is not on the boundary of P. So we've got one inclusion. The boundary of P is contained in the unions starting at big J. In the other direction, the boundary of P is closed by definition of boundary, by definition of closure and interior and all that good stuff. And by our useful lemma at the start of the video, the boundary of P, it contains the boundary of Q and the boundary of R, and then we throw out everything in their intersection. So I'm not even going to write down the lambda J is and the lambda K's for below J, because I know we're just going to throw them out. So we threw out all the lambda J's, the lambda K's, and then we have to worry about any other intersection point. So we might have a situation like this one. Here is Q. Here is R. And then we get this 1 point on the intersection, 1 point on the intersection of their boundaries that's not in a line segment. There aren't in this case, in this picture, J is 0. So we have to throw away. So the lemma says, well, to really be sure, you have to throw away all the points in the intersection. Which we can write like that. But notice that this side, this is finitely many points. And this thing over here, the thing we started with, the non-overlapping sides, you notice that every point is a limit point. So that means that you can't delete finitely many points from a set like that. If you deleted finitely many points, it would not be closed anymore. So we can't. So we know that every point we could potentially be deleting is a limit point of the stuff we have to keep. So we must have that it's equal to all of the stuff, all of the non-overlapping line segments. We can't delete any isolated points. And incidentally, that also proves that the union of two polygons that overlap only on the boundary is, in fact, also a polygon, because we've seen its boundary is the union of finitely many closed intervals. So there is the lemma we're proving, and there's what we've been able to say about the boundaries of our polygons P and Q and R. So now that we know what the boundaries are, what we're talking about, this there isn't that much left of the proof. Let's let G be this thing we're integrating over all of our polygons, because I don't want to keep writing it out. And remember, F is C1, meaning its derivatives are continuous. So G is continuous, and so it is Fubini integrable. On all kinds of nice regions, including polygons, points, and lines. Then if we remember how we defined integrating a continuous function over a polygon, that means you extend it by 0 outside of the polygon. And you can see from the definition that that's the same as integrating over Q, and then integrating over R. And then we have to subtract off the overlap, the region where we integrated twice. And now let's say a little bit about this overlapping region. Q intersect R by assumption in our lemma. That's the intersection of the boundaries. And we've just seen that that's all these line segments that show up in both boundaries. And then we have to throw in everything, the intersection of all the other line segments. All the lines that are only on the boundary of one of our polygons. And notice that these guys are all line segments. So that's J minus 1 line segments. And then these guys, if you intersect two of these, either you get the empty set or you get some points. So this is finitely many points. So you might have to be a little bit careful with overlaps again, but all your overlaps are going to be single points again. So G is Fubini integrable on that intersection. And the integral of G, it's the sum of a bunch of integrals over line segments and points. Maybe you have to subtract some points that get double counted. But the point is, everything you're integrating over, you get an integral of 0. So we can write that the integral of G over P, that's just the integral over Q plus the integral over R. And we assumed that Green's theorem worked in Q and R. So we can write this as the integral over the boundary of Q of F dotted with the tangent vector plus the integral over the boundary of R of F dotted with the tangent vector to R, where TQ, TR are the tangent vectors, to partial Q, partial R, oriented positively with respect to Q and R. Meaning if you rotate the tangent vectors 90 degrees counterclockwise, you get a vector that's pointing into your domain. And which vector is the vector that points into your domain might be different if your domain is Q and if your domain is R. And in fact, it's definitely going to be different. And now we remember that if you've got line segments, you can chain them together to get the boundary. If Q and R happen to be disconnected polygons, triangles attached to just a vertex or something, you might have to do it with 2 or more pieces, but you can work it out. And the conclusion you'll come to is that the integral over the boundary of Q, that's equal to the sum of the integrals over all of these line segments. So I'm going to write that out. All right, and then what we're going to do is we're going to split off the line segments that are in the boundary of P. And then we'll hang on to, and then we've also got all the line segments that show up on the boundary of both the Q and R. And remember, in that case, they're the same line segment. Now, let's think about what's going on with all these line segments. So if we're looking at one of the later line segments, if little j is bigger than big J, then if you draw one of the lambda j's here, then, well, we're not quite sure what's going on at the ends. Maybe we've got some other bits of the polygon and coming off, but we do know that in the middle of lambda j, we must have P and Q on one side and not the other. So that means that the normal vector, the inward pointing normal vector to P, is the same as the inward pointing normal vector to Q because they're on the same side of the line. Then the normal vector pointing into P is the same as the normal vector pointing into Q. So the tangent vector, which is the normal vector, remember, rotated clockwise, must be the same for P and Q. And a similar thing is going on the big lambda sub k's where you're going into P and R. And it's exactly the opposite for j less than or equal less than our big J. In this case, our lambda j, well, again, we might have, we're not totally sure what the boundary is doing over here, but near lambda j, we necessarily have Q on one side and R on the other side, meaning our normal vector for R pointing into R must be the opposite of our normal vector pointing into Q. And then rotate it 90 degrees, we again must have that the tangent vectors point in opposite directions. And since they're unit vectors, if they point in opposite directions, we must be going the opposite way. So we can put this all together and get that the integral over P of our function, G, we can replace the tangent vectors in here by the tangent vectors to P because they are the same. And then we notice that these two terms up here must cancel with each other because the tangent vector to R and the tangent vector to Q, they point in opposite directions. And so we're only left with the line segments that are on the boundary of P. And in fact, that's precisely integration over the boundary of P. And that's exactly what we were trying to prove. I would like to say at least a little bit about Green's theorem and integration in regions with curved boundaries. But it turns out if you allow regions with curved boundaries, you get into a lot of very messy technical geometric arguments. So and we don't have very much semester left, so I am going to look just at one very special case of a region with a curved boundary. So let's let X be the unit disk. And then the conclusion is continuous functions are Fubini integrable and Green's theorem holds. Let me quickly write out what Green's theorem is. And we will prove all of this in the special case of the circle, and you can think through when this might apply to other regions with curved boundaries. I'm going to break the proof of this up into a definition or two definitions maybe, and four lemmas, and then the lemmas will be your homework for this lecture, and perhaps some exam study problems. So here is the definition part. We're going to let gamma be our parameterization of the boundary of the unit circle. And I'm going to fix which parameterization I want, and I'm going to let gamma of t be everybody's favorite parameterization of the unit circle, cosine t sine t. And then gamma is a simple closed C1 curve. And since we've done so much with polynomials, we're going to let Pn be the polygon with 4n sides inscribed in the unit circle. There's many of those. We'll let that be the polygon with vertices. At cosine k pi over 2n, sine k pi over 2n. For k between 0 and 4n. If you include k equals 4n, then you count the vertex at 1, 0 twice, which is why I'm stopping there. And our lemmas that we're going to put together to prove our theorem is, first lemma doesn't have anything to do with the polygon at all. The first is that if G is continuous, then the two iterated integrals in the definition of Fubini integrable exist. Where G naught is as usual. The extension by 0. Second lemma is that if G is a continuous function on X, then our two iterated integrals, which we know exist, we know that those exist by the previous lemma. And we know we can integrate G over the polygon Pn. And I don't have to write out the iterated integrals because I know G is Fubini integrable on Pn. Pn is a polynomial. So this lemma is saying that this limit exists and happens to equal the iterated integral. And in fact, it equals the iterated integral in the other direction as well. And therefore, we must have the two integrals in the two directions are equal, and therefore we've proved these two lemmas prove the Fubini integrable part of our theorem. It is also saying something about the Green's theorem part of our theorem. It says that this integral over x, we can write that left-hand side as a limit of the integral over the Pn's. So to prove Green's theorem in the circle, you just write, we just proved this lemma. If f going from some open neighborhood of x to R2, a vector valued function is continuously differentiable, all its derivative is, in fact, I believe all you need is continuous. You need continuously differentiable in Green's theorem because you want again, for this quantity to exist, but to deal with the right-hand side, you only need f to be regular continuous. And we know that exists because f and t are both continuous functions, so it boils down to a one-dimensional integral of a continuous function. Where, of course, the tangent vectors depend on which domain you're integrating over the boundary of. And those are the four lemmas you'll prove on your homework and maybe on the final. This lemma may help in the proof of the previous three lemmas. So here's how this works. Let's let tk, or maybe sometimes we'll want to call it tkn, be that k pi over 2n and let's define gamma n going from 0 to 2 pi going to R2 by gamma n of s is equal to this quantity. So this, you'll notice our right-hand side is giving us the straight line segment from gamma of tk to gamma of tk plus 1. And then the conclusion of this lemma is that gamma n is a simple closed piecewise C1 curve you can reparameterize it to be actually C1 at a cost of your derivative has to be 0 at all the vertices. And the boundary of your polygon Pn is the image of gamma n. So this is just, I'll go ahead and tell you how to parameterize the boundary of the polygons we're going to work with.